I think the timer, it runs, checks, gets the return. I think it's there's one thing. I know. That's what's weird. I'm not really. I'm not sure. You know what's terrifying? I guess what the other thing is it's creating a difference.
All right, everybody, let's get started. Okay, you can pick up wherever you are after class. So today we are going to do a review for the quiz. So we're just going to go basically look back at the lectures we've had since last quiz and make sure all of that is clear. Look at the practice quiz. But before we get into that, I wanted to go through some announcements. So one piece of feedback I got on the survey is that it'd be nice if the lecture videos were available earlier. And I was like, oh no, I want to put them on YouTube because basically every once in a while the university goes through a migration to a new platform for hosting videos. So we had TechSmith Relay and all those links are broken, and now we have Panopto, and Panopto is really nice, but who knows when that will go away. So I like putting things on YouTube, but I realized that if I just organize, they have to go through Panopto anyway, and so as long as I just put them in a special folder on Panopto, then you can get them before I have to download them and put them up on YouTube. So now there's a link in Discord, but also you can find the link on the syllabus page. And so basically after class, they should just go right here. And then, within the next day, I'll put them on YouTube. But you can always follow this link and find them. And that will probably be up right after class. So you can have that. So yeah, the link, if you don't know where it is here. And it was also in Discord. Let's see. Another announcement is that for Lab 10, I'm just going to give everybody 10 out of 10 on Lab 10 and call it good, because our next project, which will be up by Monday, is going to cover stacks and queues. And so as long as you just get started on that, you're going to have you'll have work to do, but we've been pushing a lot for 10 weeks, and you can probably use 1 week off. Plus, you got the quiz next week, and we won't be covering that much new content. So, but there still will be. I just changed this. You can still go to lab, and so you could probably use that time to get a really good start on Project 4. But it won't be up. I won't guarantee that it's up until Monday morning. So, not up yet, but. Cool. Any questions about either of those things? Great. So, yeah, today for quiz review, I was just going to go through lecture by lecture and kind of review what we did in each lecture. So we started off with applications of array data structures, and the first thing we saw was the scoreboard. And I guess actually, we thought about what is a data structure. The sort of precise definition of a data structure is an implementation of an abstract data type. But generally, we think of data structures as structures that have functionality that's defined, store data, and they give us, they allow us to accomplish tasks with that data. And so in Java, these are our classes, are often data structures. And so we've done a lot of comparing arrays and linked lists, arrays and linked lists. We would say, this is kind of more just interesting thing, but we would say both our arrays and our linked lists, the abstract data type that we are trying to get at is just a list, right? Like a list of things. I can access what's the thing in the 5th spot? I can add something at the end. I can add something at the beginning. I can remove things. All of those are sort of functionality that we'd want from the list abstract data type. And then we can either choose to implement that abstract data type using an array kind of under the hood or a linked list. Would be 2 options. But before we even got to that, we saw the scoreboard, which really was kind of a more complicated version of a list, right? And what made it more complicated was that we would maintain the ranking. And so when we add something new to the scoreboard, we need to find the right place to put it. We don't just put it at the end, we don't just put it at the beginning, we have to find the right place. And yeah, really that was kind of just an intro to arrays as data structures. These can be really, as part of building data structures, arrays can be very useful. But we really focused on linked lists versus arrays. But first, okay, I want to spend some time on insertion sort. So, insertion sort, we didn't really formally study this. We'll get to sorting more formally at the end of the class. But you do need to know about insertion sort for the quiz. So, anybody want to remind me how does the insertion sort algorithm work? Or, yeah, as opposed to some other sorting algorithm. Anybody remember?
Is this the one we implemented in game entry? We do it differently?
Yeah, I guess in game entry, we basically used the fact, we always assumed that it was sorted. We didn't really sort, but we did have to insert into the right place. So it does have a similar feel. So if nobody remembers, insertion sort is, I think of this as like, insertion sort is how I sort my hand of cards, if I get a hand of cards. Basically, we start from the left, and whatever our input is, so here our input is B, C, D, A, E, H, G, F. Our goal is to sort those, and we just move from left to right, and everything, once we've processed a position, everything to our left is going to be sorted. When we get to a new position, so say when I'm processing position 1, then I just need to say, am I already in the right position? If not, then I need to move over to the right position. So for example, B, C, D was already sorted, but once we get to A, then A needs to come over and be inserted at the front. And so we're just scanning from left to right, and every time we need to move something, we just move it to the correct place, and then we move on to the next thing. You wouldn't have to answer a question like this on the quiz, but anybody have any guesses about if we wanted to make a loop invariant to prove the insertion sort was correct, what our loop invariant would be?
The letter you're working on is supposed to be to the left of the letter.
Well, okay, so let's see. So suppose that yeah, that's kind of like my decision. Do I need to keep going left? Like, do I need to keep? So first I need to decide when I get to this A, right? When I get to the A, I need to decide, does it need to move? And how do I know it needs to move? Well, it's smaller than D, right? So when I checked C, I knew it didn't need to move because it's greater than B. I checked D, I know that I just checked to my left, it's greater than C. When I get to A, it's not greater than D, right? And so I have to move it, I keep moving it until I get it to the right place, which is all the way at the beginning. And so I think you're saying my loop invariant could be something like, something about keeping moving left. I guess there's actually kind of that internal loop that could lead us somewhere for the internal loop, but at least for the external loop, the loop invariant that we would use is just that everything to the left is already sorted. So then when I get to the end, I can say, yep, everything to, like when I get to index 7, everything to the left is already sorted. And so that's how my loop invariant then allows me to prove that the algorithm is correct. But yeah, do understand insertion sort. So one way that we can check our understanding of insertion sort, just in case it's helpful, here we also have the code here. So how's that? Everybody see it? Nice. Yeah, I bet the white on the black is probably good and easy to see. So here's the code for insertion sort. Again, we just we walk starting on the left. We really just start at 1, right? We don't have to start at 0. If we look at this picture, of course B, of course we don't need to move B because there's only one element. So we start at 1. We're going to go to the end, and then this loop here is checking, do I need to move it left, and then moving it all the way to the left if we do need to move it. Okay, I have 2 questions for insertion sort. So first off, what is the big O runtime in the worst case for insertion sort? Yeah.
N squared?
Yeah, and why would you say that?
Because it's got a nested while loop.
Yeah, so the nested loops, always a great clue to know that our runtime is quadratic. Great. Additionally, what about, okay, so how about in the best case, what is our runtime, and what is the best case input? Yeah.
If you were already inputted something that's sorted,
Yeah.
it would be N.
Yeah, if it's already sorted, so why is an already sorted array going to be our best input?
Because you never execute the while loop.
Yeah, exactly. The while loop never happens, and so it's basically just a for loop walking over the array. Nice. Any questions about that? How about, is it a problem that, the first time, even if we had to move every time, this first one I only had to move 1, and the second one I only have to move 2. It's like the last one I have to do n times, but is it a problem that for us considering this to be quadratic that I only have to do, on average I only have to do half the array, say? Yeah, and why would you say that it's not a problem if I only have to go, it's like n times n over 2? Yeah.
Because you end up with half n squared, it's still n squared.
Yeah, exactly, and we would say that's because we can, the constants and lower order terms don't matter. And so 1/2, if I multiply n squared times 1/2, that's multiplying n squared times a constant, and so that's not going to affect the big O runtime. Cool. So insertion sort, linked lists. We did a lot with linked lists, and so I would just say make sure that you know what a linked list is, what are its components. It's got this internal node class. also be able to say the runtime of all of these methods, and also of methods that we haven't talked about in class. So, if I describe a method to you on a linked list, be able to think about, basically, does this require us to walk over the whole linked list, or do we already have a pointer to the thing we need to manipulate, and can we make all those changes? Yeah, in class the other day, we wrote down the runtimes for some of these methods. How about, let's see, I saw that there was this, okay, for us, if we think about this additional problem here, anybody have any thoughts about how we would, just a description of how we would solve this problem and its runtime? Yeah.
I would say we just walk through the entire list and how do we go.
Exactly. Yep. And one hint I'll give is don't be afraid to draw a picture to double check your intuition on methods for linked lists if you have time. So you've got a full hour for the quiz. And I always think that it helps me to draw a picture and say, just double check, for size, we know, for size, it's exactly right to say that this is going to be, take linear time and we should walk over everything. But just make sure that, we're going to walk over this one, and then we're going to look at this one, and then we're going to look at this one until they're null. But I think that never hurts to draw a picture to make sure that you can move your pointers appropriately. Yeah. Okay, so there's kind of our basic. Did you have a question?
Yeah.
Either of you?
Is this quiz going to be the same as last year, or is online also going to
Yes. Yeah. So, yeah. Why don't I just hop over to the quiz description? I may have updated that today. So, exactly the same. It'll open at 8 a.m. on Monday. It'll close 6 a.m. on Wednesday. And I will be here during our lecture time on Monday to answer any technical questions or clarifying questions about the questions themselves. Otherwise, you can post on Discord, but there's no guarantee that anyone will get back to you in your time. Let's see. So, yeah, same resources available. Also, this quiz, so last time there were 13 questions and 2 kind of do you understand the rules of the quiz questions? This time there are 15 questions and still the same, do you understand the rules of the quiz questions? So, 2 extra questions this time. Yeah. Okay. So we had our basic singly linked lists, but we also saw 2 variations on linked lists, which were our circularly linked lists. And so these are useful when we have problems where, it's not just when you get to the end, it's the end. You get to the end, well, we should loop back to the front again. So turn-based games would be represented like this, etc. And so a rotate method is going to move, what do I consider the front? Basically, we're just moving, what do we consider the front of the list now? doubly linked lists. I remember in our lectures we kind of suggested these for a while before we actually saw them, but since our regular linked lists, our singly linked lists only have pointers in the nodes going one way, it'd be nice and convenient if instead we also pointed backwards, and so that is what a doubly linked list does. And we also saw how if we add what are called sentinels, so basically a kind of meaningless node at the front and a meaningless node at the end, we can reuse the same logic for adding and removing nodes without having to deal with the boundary cases. Yeah.
Sentinels considered like their own nodes. If you asked us how many nodes is a doubly linked list, we could initialize with it would be 2. Or they're not really nodes, like so you still say 0.
So, yeah, I would say for a question like that, I would say that it has 2 nodes, but its size is 0. But I would definitely try to emphasize, how many nodes does it have? Yeah, I would say it has 2 nodes. Yeah.
Create the sentinels, call them null, so they exist.
Yeah, their data is null, but that is, it's still a node, it just has, its data is null. Do we have, I didn't really look. Node methods, okay. Yeah, so, yeah, we had this header and trailer node, and they actually had null data. Let's see where oh yeah, okay, the data's first. So, yep, initialize to have null data, and header and trailer are never going to have their data hold anything. Okay. Okay, then we saw a bit about equivalence and cloning. And let's see, did we draw any pictures on this day? No. But, yeah, I mean, same basically primitive data versus reference data types, just like in the beginning of the class when we were learning how to program in Java. It's important. Also, when we're thinking about higher level, we're starting to think about data structures and algorithms. We also just need to understand how reference data types work. And, oh yeah, okay, we can look at this code actually. Let's look at equivalence and cloning .java. And so we saw things like for reference data types, like our movies, when we just use the assignment operator, M3 and M1, they now point to the same object. And so, here's QuickTime. And so the picture that we'd want to have in our head, we've got some movie. Harry Potter, 2002. And M1 was already pointing to that. And then when I say M3 equals M1, I'm not making a copy like I might hope. I'm just pointing to that same object. And I realized there was a question when we were learning this, like when would you ever actually want to have two things, like two pointers to the same reference to the same object? And I realized that we actually do this. Like we've actually seen this in our code. Can anybody think of a time that we do have two pointers to the same object hanging around, at least for a little bit? Because I didn't fully think it through. But yeah.
Like if we had a double just one data node, and we want the two things to go to.
Yeah, well, one thing I was thinking was when we write things like, when we need to walk over a linked list, if we start at head, like think about our size method. If this is head, and we say current equals head, right? What are we doing? Well, you're not seeing what I'm writing, which is probably for the best. So let's make a new picture. If I have a linked list, let's say it just has three nodes. And so I have head is a reference to that first node, and tail is a reference to that. And I make a current pointer, like a current node, that's going to, first it's going to point to the front of the list, and then I'm going to say current equals current dot next, right? Or dot get next. And then it's going to point here, and then it's going to point there, right? And so when I first create current, and it's pointing to the first node, then both current and head are pointing to the same thing, right? Current and head are referring to the same data. Does that make sense? So the same picture, really. M1 and M2 are referring to the same movie object, and current and head are referring to the same node object. But we showed, okay, instead of just referring to the same object, we can also have this idea of cloning. We can have this idea of cloning, like actually making a copy. And additionally, when we check equality, the default equals operator is just going to check whether they do refer to the same object. If we want to check whether their data is equal, we need to implement that ourselves. All right, then we got on to the good stuff, I think, which is runtimes of algorithms. So we saw growth rates, experimental analysis. It's useful, but it also has some drawbacks, especially that different hardware and software, they're going to give us different runtimes. We're not going to be able to test every possible input, and we have to implement the algorithm. So we focus on how many primitive operations is it going to take, and we focus on the worst case input. And really key here is that we want to characterize the runtime over as the input size grows. And we have some functions that we are going to compare to. One, I would say make sure that you know the order of these sizes. So this is the order. Like we would say log n is a big O of log n algorithm is faster than n algorithm. So make sure that you know that. So maybe look up the definition of log if you've forgotten. So, okay. It's the next one that has some practice problems. Okay. So we saw the formal definition of big O notation, but really for the purpose of this class, we can just go with some intuitive definitions, which is basically that lower order terms and constants don't matter. It's also important that big O doesn't have to be tight. So n is big O of n to the third. Probably be some questions like that on the quiz, so don't get tripped up. So yeah, let's look at this one right here. Order the following functions by their asymptotic growth rate. So maybe instead of ordering them, let's just try to see which are any of these constant. So big O of 1. Yeah, exactly. So 2 to the 10, it's a big number, but it does not grow with n, so it's constant in terms of n. What would be our next smallest so after constant, it doesn't look like there is one in here, but what would be the next smallest big O? Like, what would be the next smallest function? Well, generally, whenever we have like an n and an exponent, that's not good. But you're right that log n, after constant, log n is our smallest growing function, our slowest growing function. But I don't think we have anything in here that's big O of log n. So, okay, what's our next? So we said 2 to the 10 is constant. What would be our next smallest function? So, yeah, okay, so these two are both good candidates. I guess the comma goes away when I highlight it. But, okay, so we got 4n. Let's take a look at 4n and 3n plus 100 log n. And actually, I'm going to pull up the... So, we got... Oh, this is perfect. Yes, you see that? So 3n plus 100 log n and 4n. So, okay, this is the easy one. So how do we write this in big O? What is this? What's the type bound for big O for this? Yeah, big O of n. I'll say. We can say, a lot of times we say is, and we can also say, equivalently, we can say 4n equals big O of n. So, okay, that's easy. That's because our constants don't matter, so we don't care about that constant. How about this one? Yeah, so this is also big O of n. And why is that? Yeah, so 100 log n is a lower order term because log n is asymptotically always going to be smaller than n. So we can ignore this, and then also, again, constant, 3 goes away. So those are both big O of n. Yeah, okay, let's do one more, just to make sure that there's one that we haven't talked about. So what are the next smallest ones?
Is it 4n log n and n log n?
Yeah, exactly. Yep, 4n log n. And we apply the same logic again. So n log n is bigger than n. It's smaller than n squared, but it's bigger than n. The 2n falls away because it's a lower order term. So both of these are n log n. Cool. I think that is enough to make sure that you are good to go for the quiz. And yeah, okay, we saw algorithm. Finally, we saw algorithm correctness. Really, the takeaways here: what does it mean for an algorithm to be correct? How do we prove that an algorithm is incorrect? And then loop invariants, they give us a formal way to make arguments about why algorithms are correct. That's really all you need to be able to say for the quiz. Any questions about the content? Feeling good? Cool. Let's take a look at the practice quiz. Just to get... What is this? Practice quiz 2. Oh. Well, no, let's take it. Take it together. Practice quiz 2. Preview? Yes. Okay. Yep, so this is what it'll look like. It'll tell you that you only have an hour to take it, but otherwise, familiar D2L quiz. And I guess they'll each be on a separate page, but otherwise, this is what it's going to look like. All right. So, cool. First question, similar to, I'm seeing some thumbs up. Yep. So don't get fooled. Just because there's a, something is squared doesn't mean that it's n squared. And just because I put the constant thing on the left instead of the right, 2n is the only thing that's depending on n, and that's big O of n. So we choose true for this one. Okay, how about question 2? Adding an element to the end of an array requires shifting all the elements of the array and then inserting the element in the correct spot. Yeah, I'm seeing the thumbs down. It does not. The whole point of using an array is that adding at the end is fast. We can just put it there, don't need to shift anybody over. So this would be false. Okay, question 3. In order to characterize the runtime of an algorithm, we're concerned with how the runtime grows as a function of what? Yep, exactly, the size of the input. And what variable name do we usually use for that? Any guesses? N is correct. Yep. Okay, select all. Oh, okay. Size of the input. Select all of the data structures for which accessing an element in the middle, meaning running getN, is constant, meaning that it requires only a few operations, or maybe even just one operation, rather than traversing the entire data structure. Well, let's go through them one at a time. How about, is this true for an array? It is true for an array. How about a singly linked list? Not true. How about a doubly linked list? Yeah, still doesn't help us. Circularly linked list, still not helped. We still would have to walk to find that position if we had a, we probably would have a way of talking about position in a circularly linked list. So, yep, so just because there's multi-select here, don't have to select more than one. And let's try it out. Hopefully we got 4 out of 4. Submit. Yay, we did it. Okay, great. So I hope you all get 100% on Monday or Tuesday. If you have any questions, you can come up, and I will see some of you on Monday if you choose to come. Mm-hmm.